The growth of phases can be either interface controlled or diffusion controlled. In the case of interface controlled growth, the atoms switch positions at the interface between the parent and product phases. So there is an exchange of atoms over a length scale, which is the width of the interface, which is the width of the interface is usually considered as about 3 interatomic distances. The other mode of by which the growth of the product phase can take place is what is known as the diffusion controlled growth. In this case, long range diffusion is necessary, so consequently solute atoms, they have to, or the solvent atoms, sometimes they have to move long distances, and then they reach the interface, but the transfer of interface is quite rapid across the interface. So consequently the slowest process is the diffusion of the atoms from the interior of the parent grains or particles to the interface. So that is the slowest step. So in this instance we call that the growth is diffusion controlled. So now what we can do is we consider diffusion controlled growth process exemplified by precipitation of a new phase from parent phase. Now consider the precipitation of new phase beta of different composition than the parent supersaturated solution alpha. Schematically we have the phase diagram here. Beta phase is rich in the solute B. So here, beta phase has got this composition, which is substantially more than the equilibrium concentration of alpha phase at this temperature. We also assume that the crossing of the atom across the interface is very fast, so that the growth rate of precipitate is determined by the diffusion of B atoms from phase alpha towards the phase beta. Figure A here shows the phase diagram, and figure B shows the free energy of the phases alpha and beta as a function of composition. So alpha has composition, the free energy varies as a function of composition for alpha in this particular fashion, and we assume that beta is nearly intermetallic constants or very close or a very narrow solid solution. So consequently this is how the free energy versus composition curve will look like for this beta. So we assume that alpha beta interface is flat, incoherent, and a local equilibrium is established, that the composition of the two phases at the interface are given by the phase diagram. That is the meaning of existence of local equilibrium. We assume that the parent phase alpha of composition C0, which is at a T1, is quenched to a lower temperature T0. So alpha phase is quenched from T1 to T0 here. So it has got a composition given by this particular point. So as a consequence, this alpha is supersaturated here, so consequently beta phase nucleates here, and when the transformation is complete, the alpha phase will have this composition, and the beta phase, which is separated from alpha, having a supersaturated solute content, will have this composition. We assume that the parent phase alpha of composition C0, which is at T1, is quenched to a lower temperature T0, where beta phase nucleates to the composition C beta. So this is the C beta composition, and then we have got C. Let the interface position be at x at time t. So this is what we are shown here. The interface velocity is u is equal to dx dt. How fast the interface is moving, so that the width or the amount of beta phase increases as the interface moves. Beta particle grows, and then alpha shrinks. To arrive at the position of the interface, we consider the mass balance of the component B. So this is the interface position at instant of time t, and this is the composition of CW. This is the composition of beta, and this is the composition of intermediate composition. Suppose the interface moves by dx at x in time dt, then dx dt is equal to u is its velocity. The quantity of B that goes into beta phase per unit area is n beta, and that is given as C beta minus C alpha into dx. So here this is more clear here. So this is the composition of C beta is this. This beta is rich in solutes B, so consequently that is what is shown, and this is the as quenched composition, and this is where you have got C alpha. So consequently the quantity of B that goes into beta phase per unit area is n beta is C beta Cl minus C alpha multiplied by the dx. During the same period, the quantity n alpha of B is removed from the alpha phase by diffusion, which is n alpha is equal to d, the diffusion coefficient capital D multiplied by dc dx. So that is the flux is given by d multiplied by dc dx, and we are multiplying with the time. So consequently the quantity of n alpha is capital D diffusion coefficient into concentration gradient of C as a function of x multiplied by dt. Now equating n beta is equal to n alpha, we have got C beta minus C alpha into dx is equal to d multiplied by dc dx multiplied by dt, or dx dt is equal to d by C beta minus C alpha into dc dx. Now assume a linear variation of C in the phase alpha at the interface. So this is beta and this is alpha, and L is here is called as the diffusion distance. So dc dx is equal to C0 minus C alpha by L. So this there is a, so the concentration in the liquid in the alpha phase is increasing from C0 to C alpha over a length scale of L. So because by virtue of the B atoms joining B, there is a depletion adjacent to of B atoms adjacent to the interface, and far away from the interface the solute concentration is equal to C0. But this variation we are assuming it to be a linear one. So consequently we have dc dx. How the c is varying as a function of x is C0 minus C alpha by L. L is the diffusion distance. So consequently, if you equate these two quantities, n beta is equal to n alpha, then dx dt is equal to the diffusion coefficient over the composition interval C beta minus C alpha, this length, into C0 minus C alpha by L. So what we have done here is we have substituted in this equation for dc dx. So this equation substituted into this, so consequently we have obtained this equation. Now if we estimate the diffusion distance L by equating the two shaded areas in the figure here. So this is a rectangular area, this is a triangular area. So the total solute content in this is in this rectangular area is the current position of the interface is x, so consequently the total 0 to x, so consequently it has moved from 0 to x, so consequently the total solute content is equal to x multiplied by C beta minus C0, which is the area of the rectangle, and that must equal the area of this triangle having a length equal to diffusion distance here and a base equal to C0 minus C alpha. So consequently the area of the triangle is half into base, height of the base C0 minus C alpha multiplied by the height. So consequently that gives the area of the triangle. Equating the area of triangle with the area of rectangle, we have got we can estimate what is known as the diffusion distance L. So substituting for L, we have got dx dt is equal to diffusion coefficient divided by C beta minus C alpha multiplied by square of C0 minus C alpha over 2x into C beta minus C0. So consequently this is equal to rewritten as d over 2x multiplied by, in the numerator, C0 minus C alpha square whole square, in the denominator C beta minus C0 and C beta minus C alpha. So if you represent this composition dependent term by means of omega, then this equation can be simplified. So you can bring x onto this side, so x and dt onto this side, so consequently x dt is becomes d by 2 into omega. So consequently yes, and then you can do the integration. So that gives the position of the interface. X is equal to omega under root dt, and the growth rate is u is equal to omega by 2 in the under root d over t, where t is the time of transformation. So the omega is seen as a measure of supersaturation, and it is the thermodynamic driving force for growth. The term square root dt is the diffusion distance and may be seen as kinetic term that is characteristic of diffusion controlled growth. So one of the significant facts is the growth rate is inversely proportional to the square root of t, and the dimension of the growing beta phase particle is varies, which is x varies as a square root of t. These are the significant outcomes of this model of diffusion controlled growth.